Ken, we can see your screen.
Excellent. Shall I go ahead?
Yes, please.
Alrighty. So I'm Ken Paulton from Keysight, and I'm going to talk about the bunch of wires interface, the 0.9 release of the proposed specification. It was intended to be the 1.0 release, but we didn't quite get there. So I'll do a little overview of a bunch of wires, parts of a link, specifications, status and examples, and our call to action. So what is it? A bunch of wires is a wide parallel die-to-die digital I/O spec, proposed PHY spec. And it's aimed at the kind of scenario of multiple chiplets within one package, and you want to have low power links between each of these. The sort of motherhood and apple pie characteristics are low power and free of IP costs and interoperable, attempting to create an ecosystem. What's different about bunch of wires? First is scalability. This will be scalable over process at least 28 to 5 nanometers, and you'll see that we've pushed that further. Next is portable across package technologies, and we see that this works in both organic laminate low-cost packages and in the higher cost interposer-like packages or similar technologies. And you end up with a lot of choices that give you a bunch of different capabilities in terms of bit rate and resulting bandwidth density. And the second big difference in a bunch of wires is that it's inexpensive, both in the amount of design required and manufacturing if you use a low-cost package. So this attempts to give an idea of the trading of data rate versus complexity. We have data rate, gigabit per second per wire on the left axis, and the trace length on the horizontal axis. And we have two basic flavors of bunch of wires. We have bunch of wires basic, and we have bunch of wires fast. And basic is, as it says, it's a simple design, and it can operate in either interposer or in organic laminate packages. And in interposer, it'll go up to 5 gigabits, and in laminate, depending on the length of your traces, it'll go 5 to 8 gigabit per second per wire. And then we have BO fast, which uses double terminations, higher gain receivers, basically more complicated analog design, but not yet to the point of needing equalizers. And that basically allows you to go faster per wire and also farther. The 2 millimeters in interposer or 10 millimeters in organic laminate basically allows you to do the chips side by side, as I showed in the previous cartoon. So what's new in BO? Since we did our 0.7 spec last year, we have defined our slice and wire ordering to simplify the interoperability. We have defined the electrical specs for both BO basic and BO fast, and the PHY to link layer interface and the external control interface and initialization. So this is giving a taxonomy of a BO link, if you will. The wires are simply the package traces that are running from chiplet to chiplet. A slice is the basic unit, and it's operated unidirectional at any given time. It has 18 or 20 signal bumps, and of course the associated circuits. The long edge of the slice is parallel to the chip edge. And then we can have a stack of multiple slices, and I've shown here a 4-stack. And if we are doing, well, the 4-stack is about 10 by 10 bump pitches, and we are not specifying particular bump pitches or even bump patterns. So the actual physical size will depend on the technology and the bump pitch that you use. Then links are stacks placed side by side along the edge of the chip in order to get the full bandwidth that you want. Now each slice operates unidirectionally at a given time, but the conglomerate of slices within a link, you can have it, half of them be transmitted, half received for a symmetric link, or you can configure it to be asymmetric, or you can configure it to be one way. This shows the wire interface of a single slice. We have 16 data wires. Can you guys see my pointer? We have one.
Yes.
Good. We have one forward error correction wire, which is optional, and one auxiliary wire, which is optional. We could use this for DBI or redundancy, perhaps other things. And we have a differential clock. And when we talk about wire ordering, what shows up in a lot of arrangements for chip-to-chip connections is that there's a northwest orientation and a southeast orientation, and ordering of the interconnects. And if you rotate your chip 180 degrees, then you end up having to do multiplexing in the silicon in order to reverse the wire order. We're doing something in a different way here. We are defining the transmit order, just the ascending order of wires, to be left to right for the transmit side, and right to left for the receive side. And furthermore, it's actually counterclockwise, sorry, for transmit clockwise around the chip on all four sides, and on the receive side, counterclockwise around the chip on all four sides. And so this naturally says that the receive slice that I have on the facing chip has the wire order agrees with the transmit side. But it also means that if I rotate this chiplet 90 or 180 degrees, the wire orders still agree. And so this simplifies the use of chiplets in a system. Something else I want to mention is I'm showing the hexagonal closest packing of bumps in this pattern here, but we're not actually specifying bump patterns in Bow. What we're specifying is the wire order, because that's all that you really need in order to be compatible with, interoperable with another chiplet. We don't even specify the bump pitch. You can have a minor inconsistency of bump pitch, probably up to 20%, between one chiplet and the adjacent chiplet, and you'll have to do some fan out to interconnect them, but you can still interconnect them. So slice ordering takes the same principle of transmit slices are numbered going clockwise around the chip, and receive slices numbered counterclockwise going around the chip. That's a requirement, but as a recommendation, we recommend that for a symmetric link that you use a checkerboard pattern, and this actually allows you to have different stack depths. I could have a 3 stack on this side and a 4 stack, or a 2 stack and a 4 stack, and the checkerboard allows you to do sort of maximal flexibility for connecting different kinds of stacks together. This 4x4 array, if we are using 130 micron bump pitch, which is sort of a common bump pitch in organic laminate, this will end up being 5 millimeters by 1.3 millimeters, and it carries 1.3 terabits, just in the Bow Basic. For interoperability, As I mentioned, we can have differences in bump pitch up to probably about 20%, since we're only specifying the wire order. We can have different stack depths and different link widths. And obviously you're not going to have optimal connections between chips that have, you're not going to have completely populated connections if you have different depths and widths, but you'll be able to connect them reasonably well. As I mentioned, rotation, and you can have different IC processes. This is eased partly by having requiring that all BO interfaces support 2 gigabit per second and 0.75 volts as the rail-to-rail swing. But then on the flexibility side, chiplets can choose what is the max data rate they're going to operate with, what are alternate voltages they're going to support. The bump pitch, the stack depth, number of stacks, whether they're going to have symmetric configuration for data flow or asymmetric or unidirectional, or have individual slices be capable of going either way, and you can configure it at runtime. And finally, the package technology, varying types of organic laminate or interposer-like packages are possible. The link layer of a single slice is mostly just reflecting the physical wires. Of course, we're operating at a lower rate here. We're operating at the core clock rate of the IC, and so these wires get multiplied by whatever the ratio is between the line rate and the core rate. And there's some control and status. Now, one of the things that's unusual in BO is the way we're doing control. It's common to have control for a link either transmitted over the data wires or run as a sideband interface, essentially a physical set of additional wires, which are part of the PHY, but running essentially a separate protocol. We decided that was extra complication and that it would be simpler to place the controller outside the PHY and the link. And the controller can be on one of the chiplets, or the controller could be outside the package. That's an implementation choice. Either way, when we have connections from chiplet to chiplet, there will be at least one. Then we are recommending an I2C or I3C interface from chiplet to chiplet. You need at least one controller to connect up a link, but you can have one controller operate all the BO links within a whole package. So it's not like there's a lot for it to do. So that could be something shared over the whole package. Electrically, our simulations show a very open eye for BO Basic, and one of the things that we allow is a fair amount of slice to slice clock skew. Within a slice, we're using the source synchronous clock, and with a small number of data wires, we don't have to do per bit deskew. And then we allow a relatively generous amount of skew from slice to slice, and the source synchronous clock allows us to tolerate that. So this shows PHY characteristics. The first column is BO Basic on a low-cost package like an organic laminate with example bump pitch of 130 microns. And depending on length, you might be going from 2 to 5 to 8 gigabit per second. And we can have a max data rate density of 400 something gigabit per second per millimeter. That is density along the edge of the chip. If you use a BO Basic in a dense package, you might be using 40 micron bump pitch. And we get about double that data rate density along the edge of a chip. And with BoFast, again, BoFast only operates with the laminate packages, but we're able to operate up to 16 gigabit per second, and so we get, again, 800 something gigabit per second per millimeter. The energy in all three cases is between 0.5 and 1.3 picojoule per bit, and it depends on the IC node and the voltage swing that you choose to use. Bit error rate, we think 1e minus 15 will be easy to meet without FEC, and 1e minus 25 even with a simple FEC. There are two example implementations. One is a 14 nanometer test chip that was actually fabricated. It had multiple modes, but in the bow-like mode where it was unidirectional and single-ended signaling, it ran well over 16 gigabit per second per wire and used 0.9 picojoule per bit. In old school 65 nanometer technology, we've done a simulation study looking at the main blocks, making an assumption of 3 slices stacked, and we determined we would have wires up to 6 millimeters. We were assuming 4 gigabit per second, and we came up with 1.3 picojoule per bit in that 65 nanometer process. Bow Basic is designed to be simple to design. It uses rail-to-rail I/O circuits. It uses a small 16-bit slice, so there isn't much skew from the clock to the data bits related to that clock. Because of the source synchronous clocking, there's no CDR. Because of the short links, we have a wide open eye, so there's no equalization required. The analog circuits are pretty minimal. There's a transmit driver that is source terminated. There's a full swing receiver on the other side. There's a delay lock loop. It can be other means, but the most direct thing is a delay lock loop in order to align the clock to the data. But there's only one of those required for a slice. We don't need to do it for each bit. Duty cycle correction may be needed, and somewhere we need to get that DDR clock for 2.5 gigahertz for a 5 gigabit per second data. And the control interface is just I squared C or I cubed C, something that'll be available. So the result, we think, is smaller design effort to design from scratch than porting a high-end SerDes, and considerably lower risk. We are almost at having our 0.9 version available, and it'll be on the ODSA website. This is the work of about 15 companies, and as I mentioned, we have those one test chip and one feasibility study. So to summarize, Bow is uniquely designed to allow the designer to make trade-offs in speed, chip technology, package technology, dimensions, and design complexity. It's the only I/O proposal that we know of that supports the inexpensive organic laminate packages. And it's simple to design, and the 0.9 proposal is almost available. We can use help reviewing for the 0.9 spec, and then we'll be working on finishing the 1.0 spec and expanding in the future. There's work on a test chip that's being planned, and for more information, website or Boppy's email. And this lists the people that have been contributing to this. I hope I got everyone. Thank you.
Hey, Ken. Bobby, do you have any specific questions for Ken? I'm looking at the chat here, and I don't see any specific questions popping up, but maybe you have some comments or questions.
So Ken, do you, if since we have some time, do you want to spend any cycles on what we sort of left out, saying we'll come to them in the next rev of the spec? What's next on our what we're thinking of in terms of after the 1.0 or the 0.9's baked in?
I've been more focused on what we need to do to get to 1.0. So there's bidirection. One of the things that is interesting is slices which are bidirectional in a choose the direction you're operating in, and something that was actually demonstrated in that 14 nanometers test chip was a full duplex slice that was actually able to transmit both directions at once. So those are interesting directions for expanding this in the future. That's all that comes to my mind at the moment, Bobby. You may have other thoughts.
Well, we burnt a reasonable amount of cycles on routing and making sure routing was easy. That maybe flesh that out in more detail and bring up an initialization.
Yeah.
Well,